actually looking at the calendar. I had the calendar up, didn't realize I didn't have the screen share on, but you guys see the screen share now? All right, so I made this up because there were a few questions on, and I felt like, there's a little bit of detail that I just want to go back over. So in terms of modeling the error covariance structure and how we do it in SAS, and I keep saying this, but R is something that it's not like I want to just have the class done in SAS, but really this, the curriculum, the class material was built around SAS, and now I'm integrating R and R more into it, and people like Jonathan are helping me do that, suggesting different packages and stuff. So I really appreciate when you guys do that. You get a lot of brownie points for that. So maybe nothing formal, but we're still working on that Chronica product though. We still don't have that one. So as far as the repeated statement, that's how we modeled the error covariance structure, or the R structure, we call it a lot of times. Get rid of this. So we use the repeated statement, and we know that the common thing that we use that for is for serial correlation. If you have day-to-day correlation that you need to address, like with the AR1 structure or something like that, that's commonly what we use it for. So there's some funny things about the repeated statement if you look at how you use it over different procedures. Like for example, for proc mixed, we put subject equals on the right side of slash, but in GenMod, you actually put it on the left side of slash. I don't know why there's that difference there, but that's just the convention they have. We know that in mixed, if you look at the SAS documentation, there's actually a lot of repeated structures, a lot of R structures that you can model. And even just the spatial structures alone, there's like 10 at least different spatial structures, or somewhere in there. And there's a lot that we haven't talked about, like there's just various structures. And I would suggest that, like in your project, you might look at some of those other ones that we haven't talked about. And one of the reasons why is what they aim to do is to allow you to be flexible and yet not use very many parameters. So there's some structures that may work for your data. And so I'm okay if you explore a little bit with that. Now, the data that you have, the questions that you ask, you already should have in mind kind of a subset of structures that you want to look at. So I wouldn't necessarily try everything, but you might make a short list and then maybe look at a couple other possible structures you can use, and kind of depends on the data that you have. But if you have any specific questions on that, feel free to ask me. So in mixed, we have a lot of structures, a lot of potential error covariance structures that we can use to model the data. In GenMod, there's actually not very many. There's like 3 or 4. There's the unstructured, there's AR1, there's, they call it exchangeable, which is essentially compound symmetric. But we don't have very many. So the question is, if you have intermittent data, if you have, or missing data, like if you collect data and you don't collect data over the weekends, you just collect it on the weekdays, how can you account for those gaps? Well, essentially you have to fill out your data set so that you have consecutive days, and then put missing values in for Y, and then fill in your time variable. Obviously you need that. And then use AR1. That's the way you do it for Proc GenMod. And so that distinguishes GenMod from mixed. And there's a question on the homework that relates to that, but that's how you have to do that. Some other, let's see. For GLIMMix, which is generalized linear mixed models, we know that there's 2 basic approaches that we can use. We can use quadrature to optimize the true likelihood, but it's an approximate approach because we're using quadrature. And the other general approach that we can use is pseudo likelihood, which we learned last time. And that's where we transform the data so that we can employ linear mixed models. And we do an iterative procedure and the answers converge to a solution. But the beauty of it is that we can utilize then whatever linear mixed models have to offer. So that's kind of why I like that approach. So we really have three ways of modeling non-normal outcomes where you have correlated data or longitudinal data, right? We have GEE, we have generalized linear mixed models with quadrature, and we have generalized linear mixed models with the pseudo likelihood approach. Those are three basic ways. And in proc-limix, if we're going to use that pseudo likelihood approach, there's actually not a repeated statement. The way that you do it is you add a random residual, but that's essentially like adding a repeated statement. And you can use whatever types of structures you have for mixed, you can also use here. So the last thing I wanted, this was actually one of the main reasons why I wanted to talk about the repeated statement. This is the key thing here. And I mentioned this before, but I'll mention it again. It's worth mentioning twice. If you sort your data by subject and then by time, you don't have to say what the repeated measures are on. Okay, usually it's going to be on a time variable, like day, or maybe it's time, actually called time. But you can put that in there, so you'd say repeated day or repeated time. But as long as you sort your data by subject and then by time, then it's going to just look, it's going to know that, you know, that it's going to just take whatever consecutive measures that you have for that subject, and it's going to model that. So typically I don't put in a day or time, but honestly, it's probably a good idea. I've gotten in the habit of sorting the data. And so that's why I don't put in a day or a time right after repeated. And then I just say, well, this is on subjects. Repeated measures are on subjects. So you say on the right side of the slash, you say subject equals ID or whatever identifier you have. So I just wanted to mention that again, just to emphasize that point. Any questions on that or syntax that we use? So this is really for SAS. Are there any issues for those R modelers? Any quirks that you have to deal with in coding the software for repeated measures that anyone like Jonathan or anybody else that wants to bring up that you found? If not, it's okay. We can talk about it more later.
I think I get a problem when I use the Gauss quadrature, and normally we need to set up the like a
Hold on, Randy.
value.
Let me, I couldn't hear you too well. I turned up my volume a little bit. Can you repeat that again?
Oh, sorry, it's about the Gauss quadrature part. Just like how should we find the value for the parameter? Because there is a parameter ask us about the knobs.
The number of quadrature points?
Yeah.
Yeah, that's a good question because in SAS, we don't have to worry about it because it does adaptive quadrature. And so we don't have to tell it how many quadrature points. In R, I think you do have to worry about it. The reality is, like, even if you just use one quadrature point, which is the Laplace method essentially, you probably will get reasonable results even with one. What I've noticed is that the best number of quadrature points, at least from the data sets that I've looked at, tends to be around 7. So I think honestly, but I don't know, I think you're just going to have to use a little bit of trial and error, and see the sensitivity of the convergence
Yeah.
as
Is
you move
it
forward.
the more the better? I mean, can we just like saturate it? Always use the highest one?
Yeah, the highest one is better, but you know, may take more time to
Yeah,
converge.
yeah.
So
I think
there's not really a downside in terms of numerical results. There's not
mhm.
really a downside to using more. It's just that it's more, you know, computationally intensive as you increase that.
I think in
So
R, the best we can do is like 25. The highest value is
yeah,
20.
and that I think that would be very good approximation, you know, because that's much higher than what I've seen the adaptive quadrature select. So
Thank you.
25, you know, and it could also depend on your specific data. If you have a lot of data, you know, you may have to compromise a little bit. Um, but it probably will take a little bit of trial and error if you're using R. Um, Jonathan mentioned a package and function for generalized linear mixed models that he thought worked better than um, the GLMM PQL. But the question is, does it do pseudo likelihood or does it just do quadrature?
So it does maximum likelihood and restricted. So it does ML and RAML using a template model builder.
Okay, but do you know if it does pseudo likelihood estimation?
I don't think it does pseudo likelihood.
Okay, so it's like the quadrature approach.
I think so, yeah.
Okay, but I'll take a
But
look at
it's
it.
not really the quadrature. The approach is called a template model builder.
Huh.
And
I'll have to look at it.
I sent you the documentation that tells you exactly how it works.
Yeah, which I haven't read yet. I was enjoying the weather outside over the weekend instead. I will take a look at that though.
I think there is a specific package to calculate pseudo likelihood.
Yeah, and that, I mean, the one that I know of is what I mentioned um, is the, so let me just write it down. So get this thing working here. Gotta have my pen. For some reason it's not, let's just try. Okay, we'll just pens. Well, it's called GLMM PQL. That's the one that I know of, and that's penalized quasi likelihood. You know, like I said before, they use different names. I call it pseudo likelihood because I don't want to use quasi likelihood. We already have that term that we use for something else. But that's what the R package is, and that's the one that does the pseudo likelihood. But the question is, how accurate is it? I've seen that in some cases it doesn't work as well. In some cases it does work. You know, I have got it to match SAS. In other cases it doesn't seem like it works too well. But you know, it could be that playing around with the convergence criteria and different things, maybe you could get it to work better in the cases where it doesn't seem to work well. But that's the one I'm familiar with. I took this home and so let me just get out of this. Maybe I can get this to work on a different document. I'm hoping. I'm not sure why. Really like to have this pen working. If not, it's okay, but
And I think I have another problem, but we can talk about this later.
Yeah, go ahead while I kind of play around with this.
For LMER function, we cannot get the p-value directly. And I wondered how we can calculate that by hand.
So you get your estimate and your standard errors,
Yeah,
and it doesn't give you the p-value.
yeah, for LMER, it doesn't have a p-value. I mean,
Yeah, and
yes,
my guess is I think I know why.
yeah,
You know what the issue we talk about with
nested. Um,
well, like what I was thinking of was the issue about what do you need in order to get the p-value? Okay, you have your estimate, you have your standard error. What else do you need?
um,
This is for anybody.
Denominator degrees of freedom.
Exactly. And we know that there's an issue in terms of the methods, you know, in order to, we estimate them, right? We estimate the denominator degrees of freedom in order to get the right distribution, you know, so that we can get our p-value, right, by looking at the area under the curve beyond our test statistics. So we can build our test statistic, you know, using the linear mixed model methods easily, but in order to get the right distribution, we estimate the degrees of freedom. And I think they didn't want to worry about that. So they don't give you degrees of freedom. You have to do that. You have to, I think there's ways you can do it. And, you know, maybe Jonathan, you can tell us too, with the m-means function, right? That there's ways that you can.
Right. Even the LMER test will give you the Satterthwaite.
Okay.
Degrees of freedom.
And I like the Satterthwaite. The Satterthwaite and Kenward-Rogers, I think are decent.
Right. And then
ways
there's a
to
package
estimate.
for the Kenward-Roger. There's a package called what was it called? It was called PBKR test, and that works with LMER, and it gives you the Kenward-Rogers degrees of freedom.
Yeah, and those I like those methods because they tend to be conservative, you know, and statistically conservative methods I think are good because if you can show significance, even with that, then you can say, well, even if we had used a more liberal method, the p-value would get even smaller, right? So I like you know, those approaches I think are sound. Using Satterthwaite or Kenward-Roger I think are good degrees of freedom approaches. To get those in SAS, you can get those easily, but you have to specify it because the defaults are the between, within, and the containment, you know, depending on what, you know, combination of repeated and random statements you have in your code. So yeah, some good questions. Today we're going to talk about ordinal logistic regression and mixture models. And I don't know if this is going to apply to anybody's data or projects, but maybe as you read, you know, as we go through these slides, you might be able to see how it could apply to your data. And if it does, you know, it'd be great if somebody was able to utilize these methods for their project. Especially if it's pretty clear that your data are similar to this. If you have an outcome that's not normal, but it's not binary, it's not count. If you have an outcome that's ordinal, okay, so you have several levels to the outcome, but there's more than two, and you can put an order to them. You can apply the methods that we're talking about right now that we'll talk about here in a second. Ordinal logistic regression. We can also account for correlated data, and the way that we will do that is to add random effects to the model. So here's a case study, and this is an actual data set that I've worked on here at National Jewish. I worked with somebody in occupational medicine, and they have some grants looking at subjects who are deployed to Iraq and Afghanistan for military service. And the research that they're doing is essentially trying to understand what exposures do they have. You know, like these people are often around, you know, burn pits and things where they're burning who knows what, you know, things that, you know, you probably wouldn't suggest burning. And so the question is, you know, what kinds of exposures and what levels of exposures do they have in these situations? And then how do they compare to people that aren't? Okay, so we've actually looked at samples from their lungs, you know, to try to understand what are they breathing in? What types of metals have they breathed in? And so this research has been pretty important. There's different job functions that people that are deployed have. You know, some are in infantry and some have more administrative type of jobs. So there's a wide range of job types that people have when they're deployed. And there are actually 38 classes, and we're just trying to understand for these different classes what is the exposure that we assume that they have, and then later on we're going to actually compare, you know, if we can, the predicted categories of exposure, high, medium, or low, to if we can have them wear a monitor to actually see if it matches what they're exposed to. So, you know, when people go into the military, it's good to know, you know, you can expect this type of exposure if you have this certain job type. So we had 5 doctors rate what they thought the exposure would be based on their understanding, and 2 of those doctors were actually employed. One that I work with here, who was in the military, and another who was came through here and had like a postdoc position, and then the others were just, you know, regular doctors. But all of them, we used all of them to try to assess what they thought the exposures would be for different job types. So we have this situation where we have several raters, and we have the military job type. Yeah, I'm gonna have to figure out what's going on with that, but somehow it's not. Tools. Huh. So this is kind of gives you an idea of the type of data that we have. You know, the exposure level could be 1, 2, or 3. So that's the outcome, and you see that on the interior here. So the first job type is personnel and administration. So it's not a surprise that they would say low, that they would predict low exposure for those people. Intelligence, mainly 1s as well. Infantry, they're expecting high exposure. So it's kind of intuitive to see what they're rating these job types. And then we have raters crossed by job type. So these are crossed factors, right? And if we add random intercepts, then we have crossed random intercepts in our model. But the question is, now we have a different outcome. It's not just binary, it's not a count, it's an ordinal variable. So how do we model this? Well, we can use the same type of procedure that we had before, but we have a different link now. It's similar to a logit link. In fact, it is a type of logit link. It's called a cumulative logit link. And you can see how it's expressed here. So like if we had the regular logit link, I'm just going to open another Word just to see if I can get this to work, at least in a separate one. For some reason, it's not. Okay, I give up. I don't want to slow things down too much. So it's like a regular logit link, but it's cumulative because we have multiple levels that we're dealing with, right? So the regular logit link would be probability y equals 1 here, and 1 minus probability y equals 1, or probability y equals 0, right? That would be the regular logit link. So now we have multiple levels in the outcome that we need to deal with. And so in order to account for that, we have the cumulative logit link. So we're looking at probability y is less than or equal to 1, 2, or 3. And then in the denominator, 1 minus that. So it's an odds, right? We have an odds, and we have log odds here. So we call that the logit link. And so we're going to have the random effects, BI and BJ, and those are going to count for rater and MOS type. And then we're going to have a fixed intercept, but we have actually 2 of them, right? Because if we had 2 levels, we could get by with 1 intercept. If we have 3 levels, now we need 2 intercepts. In general, we need k minus 1 intercepts for an outcome that has k levels to it. And it's actually easier. What I found is it's actually easier to flip it around and look at, if you flip around the inequalities, it's easier to look at the logit in this way. And you can do that very easily in the software. If you just state descending, then you're flipping it around. And so you're comparing probability y is at least a certain level to 1 minus that. And so for generalized linear mixed models, we know that we condition on the random effects. And so we'll be able to get subject-specific estimates for those random effect deviations. And we'll also be able to estimate those intercepts as well. Some questions of interest for our data. How do the variances for raters compare with variances over the job types? Are there any raters that significantly differ from the group average? And we can get that if we, in our random statement, if we add solution, then we automatically get t-tests to see the deviations and see whether they're significant for individual raters. And we can also do that for job types. After adjusting for cross-random effects, what are the cumulative odds of low, medium, high exposure for a given inhalation hazard? We're just going to look at burn pits for our example. What is the probability of a particular job of having high exposure to given exposure type? So we're going to fit this ordinal logistic regression model in order to answer these questions. Before I do this, and I've said this before, that even if you have a complicated model like this, what I suggest is in step 1, just do some descriptive statistics to understand your data. So whether that's using, means and percentiles, standard deviations, just get an idea of what your data looks like. And then not only does that give you kind of an understanding of your data, but it will also be something to compare against when you fit these complex models. You want to be able to see that your results make sense. And we'll talk more in a second about why do you even fit the complex models. If you can do it descriptively, there's many reasons. So we'll talk about that here in a second. But across there are 115 MOS or different job types that that the military had. And almost 2/3 of the time, the exposure was expected to be low across those job types. And it was only high for about 7% of them. So what I did was just calculating odds, the odds of medium or high classification compared to low, 0.6, the odds of high versus medium and low, 0.076. So we have a way to compare our results here in a second to descriptive results. Okay, so the code that we use, we can use proc limits or fitting a generalized linear mix model. And I'm using method equals Laplace, and that's essentially like quadrature with one quad point. Move this down just a little bit. So you can say method equals Laplace, or you could even just say method equals quad and then specify one quadrature point. It'd be the same thing. I put the descending in order to get to flip the inequality in the cumulative logit. I tell it distribution equals multinomial, and the cumulative logit link, I think, would be the default anyway, I believe, if you say a multinomial. So pretty straightforward code. And then we have our cross random effects by adding the job type and rater as two different features that we're going to have the measurements taken on. And I put in the solution in order to get those tests that we're interested in looking at. Okay, so it tells us the highest level, there were 13 occurrences. With medium, there was 56, and with the lowest, there was 115. What do the variances tell us? Well, you look at job type, and it's about 3, and rater is about 0.7. So would you think that that is encouraging or discouraging when you look at those relative variances? It would be, like I said here on the right, I think it would be encouraging because this indicates that the raters are more consistent, at least relative to the variance that we have for job types. If you had this rater variance much bigger, and let's say it was bigger than the variance for job types, then it would be, you'd want to talk to those doctors and say, look, you guys aren't really being very consistent with each other. So it's one way to assess how good the raters are in terms of consistency with each other. We have our two intercepts here. So our fixed effects, we have our two intercepts. The first intercept is going to compare the highest level to the lower two. And then the next one's going to compare medium and high to low. So if we exponentiate those, then we can get the odds of high versus medium and low, and the odds of medium and high versus low. And those turn out to be high versus medium and low is 0.02, and medium and high versus low is 0.46. Okay. And here's our random effect estimates. We have our 5 doctors. 4 of these actually work here, or they're affiliated, and then Pepper is, I'm not sure where he's at, but he was that postdoc that came here. And so we can see the doctors that tend to just think that there's lower exposure. So Gottschall tended to score lower and say no, they're being exposed to lower amounts. And Pepper and Meehan tended to think that they had, these job types had higher exposure. And what's why that's sort of interesting is because those are the two that were actually deployed. So, you know, maybe they have a better understanding that certain classifications actually get more exposure than what doctors think here. And then, you know, marginal significance for two of them. And then for each job type, we can also look at those and actually do tests of significance. 3 was infantry, right? So this one was move this down just a little bit more. So 3, this one was infantry. Maybe I can add it here. And so it's much higher, and that's not a surprise, right? We would guess, even probably you and I would expect higher exposure for people that are out in the field more, and maybe they have to go to the burn pits more and things like that. So, and it's highly significant. So it's kind of an intuitive data set. Really is one of the reasons why I use this. Question?
Yeah. So for the random effects for this model, you would have like 115 or however many job types, that many random effects. Is that right?
You have, if you go back to the grid, this one here.
Yeah.
Yeah, so yeah, we go out to 115 columns, and then you'd have 5 raters. So you get a random effect. You have to consider the marginals, right? So it'd be 115 random effect estimates, 1 for each job type, and you get 1 for each rater. So there'd be 115 for the job type and 5 for rater.
Do you ever worry like, oh, that's like too many random effects?
No,
Okay.
I don't. Now, I'm not saying it's because you shouldn't. It's just that I haven't. I haven't worried about it. And I don't, do you mean in general, or do you mean relative to the amount of data that we have?
Yeah, like relative to the sample size or something, or yeah.
I don't believe it's going to be a big issue. I mean, I think a lot of times, like if you only have, and I can feel another question that I have coming on, even to preface what I was going to say, which is, when do we use random effects versus fixed effects? So this is kind of a review question.
Well, when do we use them?
Would it be a problem if we made this a fixed effect and we had it as a class variable?
I think so. I think it would just be too many levels. Right?
It seems like it would be. Yeah, seems like you'd have a concern about how many levels you have as a fixed effect. But what kind of guides our decision about using a random versus fixed effect? That actually may be one of them. The number of levels that you have might impact you, and I think, you know, if you have a lot, usually we think about using a random effect versus a fixed effect, right? Because then we'd be adding so many parameters to the model. Here we're not. What are we adding in terms of number of parameters to the model? What are we adding? Do we add 1 for each random effect?
No.
No. What are you adding in terms of parameters? What are you adding?
It's more about the covariance parameters, right?
Exactly. Yeah. So you're adding a variance parameter when you add the random intercept. You get specific random effect deviations, but you're not adding a parameter for every rater, right? You're just adding a variance term.
Okay.
You get random effect estimates, but those are not parameters. So that's a key answer, I think, to your question, that I think we're okay, even if we have a lot, because we're not adding parameter for each job type in the model.
Yeah, that makes sense. Okay.
Yeah. Just to follow up the thought though, when do we decide? Let's say we're not worried about the number of levels that we have. What's another reason why we decide to model something with a random effect versus a fixed effect?
If it's like more about the structure of your data, so if it's clustered or correlated or something like that, right?
I think it has more to do with the conceptual element, really. Any
Okay.
other thoughts? I'm
Well,
not
for
saying
this
you're
data,
wrong, but I'm saying the main point would be more conceptual. Carrie.
for this particular example, because we don't have any fixed effects, we're just spitting out population marginals. So it's answering the question, like for me, it comes back to our question, which is just what are the population marginals, not comparing one to the other, right?
Yeah, so if you want to make your inference over any possible job type, so you're thinking about these different 115 different job types, and you consider that as a sampling of the range of possible job types that you could have from a population, and you're not really interested in specific inference for that, then you model it as a random effect. Okay, but if you want to do inference on specific job types, and maybe that's the case, maybe that would be of interest here. It kind of depends on the research questions. Then you would use it as a fixed effect. Okay, so so there's two considerations we have here are we have a lot of job types, so it seems like using the random effect approach is better. Does the model that we fit, this particular model, allow us to answer the questions that we had, or research questions that we laid out at the beginning? We had like 4 or 5 questions and we laid those out. Does this model allow us to answer those questions? I think it does, as long as we're not worrying about comparisons between specific job types. Like let's statistically, we want to compare infantry versus, administrative. And if you want to statistically compare those, and it's of meaning to do inference on those specific levels, then we might want to use it as a fixed effect. But we would have to worry about, we'd have to worry about how many job types there are, and possibly maybe combining some together or something into meaningful categories. Okay, so in terms of the results that we have here, I mentioned this, so it was looking at the output. We looked at odds of high versus medium and low, or medium and high versus low, and we can get those. We looked at specific random effect estimates.
Hey,
We
Matt,
can
can
also...
Hey, Matt.
Benjamin, so Benjamin and then Jonathan. Benjamin, go ahead.
Yeah, based on what you mentioned about inference that would fit when you're interested to make inference about comparing those job types. So I think is it one slide below or up? I don't know where we have those outputs. Yeah, this one. So how do we say that we expect infantry to give us that that p-value, yet we are not comparing the job types?
Because what we do with our random effects is we are considering deviations from the population average. So we're comparing infantry to the population average, and that's our test. So the way we set up the model, we assume that there's some population average. And the way that we assess that in this model is just by including intercepts, right? The fixed intercepts. And so the random effect estimates are just deviations away from those fixed intercepts. And that's the default t-test that we get. Yeah, so
Okay.
good question. Jonathan, did you have a question?
Yeah, if you go back up to your covariance parameter estimate, do you have to worry at all that your standard error for your second intercept is almost as big in magnitude as your estimate? So for the radar, your standard error is almost as big as your estimate?
That's a really good question. What I am mostly concerned about, like if we do, you know, I think I may have mentioned this before, you can do tests of significance for covariance parameters, and I typically don't do that. What I'm focused on more is, does that source contribute to the variance of the model, and does it improve the model fit? So like if I saw a value near 0, I would say I probably don't need that term in the model. You know, a value of 0.7, you know, relative to the variance for the job types is much lower, but it's not magnitudes, like high magnitudes lower than the job type. If you were to do a test, it might tell you that's not significant. But by looking at that already, just looking at it, it seems like it's non-negligible. And we could also look at the overall goodness of fit statistics to see. My guess is it improves the model fit. So that's what I would go by, rather than, you know, I mean, the standard error, I'm not saying it doesn't give us any information, but I wouldn't worry about it too much in terms of, should we include this in the model or not? What I'm going to do, actually, I'm not going to spend a lot of time on the rest of the slides here because I want to be able to get to our other slide set. But what we can do, we can, just like a regular logistic regression model, we can get, instead of odds, we can talk about probabilities. So we can talk about cumulative probabilities. So the probability of a high classification, 0.02, we can derive that analogous to how we derive probabilities out of a regular logistic regression model. And we can also get specific probabilities by taking the difference of cumulative probabilities. So we can get those probabilities that we want out of the model. I'll let you read some of the other details. One last thing I want to mention here is, if you just look at our original descriptive statistics and you look at the proportion of job types that were estimated to be high, is about 7%. And if you take the model approach, you get 2%. And that seems kind of off, right? Why is it different? Well, what I did was I actually took out the random effects just because I wanted to see if we were doing the model correctly. And when I took out the random effects, I actually got the same in the model as I did as descriptive. So it seems like by taking the correlation into account and by adding those random effects, it alters that probability. So it's not that we did anything wrong in adding the code. It's the fact that we had those random effects. Our estimate of the probability of high exposure would actually be lower in our inferential model than it would be in the descriptive approach. So I did this kind of as a check to see if we did the model correctly. There's some other detail. We can add covariates into the model. That may be of interest. And I talk about the proportional hazards assumption. So I will let you guys finish reading the rest of these slides and some of the detail that I jumped over here, because I want to jump into the mixture models, which are really cool. I say that about everything, I think, but either it's cool or it's really cool. Okay, kind of a nerd, but you know, this I enjoy this stuff, and especially weather and climate data. I'm sort of attracted to those things personally. We all have our own interest, right? But this is something. This is another data set that is fairly intuitive, so it's also kind of fun to talk about. So we may have situations where we don't have one distribution that's going to model our outcome adequately, right? A lot of times we can say our outcome is normal or approximately normal, or it's a binary outcome or a count outcome, or now we've learned about ordinal outcomes, how we can model those. Well, maybe it's a combination of things, and maybe one distribution is not going to adequately model our data. So we're going to talk about now mixture distributions. And you can mix different types. You could have a mixture of discrete distributions. You could have a mixture of continuous distributions, or you could mix a discrete and a continuous distribution. And that's what we're going to talk about here. We're going to talk about, specifically, we're going to talk about 0 plus continuous, because you see this a lot out there, and you may come across it if you're dealing with healthcare costs. You know, if you work at the VA, they do a lot of research on healthcare costs. And does anybody in here have data like this, that you're dealing with data like healthcare costs? I'm trying to remember if anyone had this. Precipitation amounts. So both of these have possible values of 0, right? So there's an actual value of 0, but otherwise it's positive. And when it's positive, it's essentially continuous, right? Rainfall amounts is more clear, it's continuous. With dollar amounts, you know, you go to pennies, right? Which is essentially, you know, it's essentially continuous. So we have situations where we may have a positive amount, but you could also have a 0. And the problem is continuous distributions, you assume that you don't have any probability on one specific value, right? In order to get probability out of a continuous distribution, you have to look at a range of values. So that's the problem that we're facing. Now, when we model positive amounts, some of the key distributions that we have are the log normal, we have the gamma, we have the Weibull, and truncated normal. There may be others, but we know of at least 4 that we can use for positive amounts. So what we're going to do here is we're going to say we have a probability of a 0, and we could have a positive value. And when we have a positive value, we're going to maybe use one of these 4 distributions. We're going to mix those together. So some interesting questions that we may have to ask with the healthcare costs. What is the chance that someone will incur a cost? What is the mean of costs for those that do incur a cost? And what is the overall mean, taking into account both sources, if you have a cost or you don't? And when we're talking about rainfall, what is the probability of rain in a given city on a given day? What is the mean rainfall on days when it did rain? And what's the overall mean rainfall? So we want to combine information, whether or not it rained or not. We want the overall average, right? So those are things that we may be interested in finding out. So we can get a cumulative distribution function. And so I use capital F here instead of little f. The little f is going to be either the probability density function or the probability mass function. A lot of times we use the little f for the continuous, so the probability density function. And the capital F indicates a CDF, so you're accumulating probabilities, and this is easier to work with if you have a mixture distribution. So we can essentially, with the theorem on total probability, we can consider the cases where there's no rainfall or no cost, no healthcare cost. That's R equals 0. And when there is rainfall, or when there is a healthcare cost. And so we can easily write our cumulative distribution function when we have a 0 plus continuous case. And this is the general formula for it. The problem is when we make our likelihood, we need to work with the probability density function or the probability mass function, or some combination of that. So technically, for this 0 plus continuous, this is the density function. So this delta is defined to be 0 when y is not equal to 0, but it integrates to 1 over all y on the real line. So it's a weird math thing. But we technically, the probability mass function doesn't put any probability on a specific value. And that's one way of getting around this, right? So this is our math definition for our PDF/PMF. But we need something more practical when we write our code and we maximize the likelihood function. We actually have to put in, for practical purposes, we set that term to 1. Okay, so that we can work with the tangible likelihood function. Although this is technically not a mathematical PDF/PMF. Okay, so our outcome, we're going to actually use, we're going to consider the rainfall data, and we're going to use the gamma distribution. So we have positive density for positive amounts. And for those in theory, you're probably familiar with the function that we use for that. The gamma function looks like that. The mean of the distribution is theta times lambda, where theta is a shape parameter and lambda is a scale parameter, and the variance is theta times lambda squared. So here's our model that we're going to use for the rainfall data. We have occurrence, so that means did it rain or not in a given city on a given day. And so we have a logit link for that, and we have a fixed intercept for the rainfall amount. So that's going to be our intercept across all of our data. So there's going to be some average or intercept level that we estimate. And then we're going to have a random intercept, which will allow certain cities like Seattle or places where it rains more to have a higher value, and places like Phoenix, where it's drier, going to have a lower value. So their deviations are going to depend on the climate that they have. And then the intensity part of the model is if it did rain, so given that R equals 1, so R is did it occur or not? If it did occur, what is the amount of rainfall that we had? So for our generalized linear mix model, we condition on random effects. And so in this part of the model, I'm specifying deviations off of the shape and the scale parameters. And so each city is going to have their own unique distribution of rainfall amounts that's going to be estimated. So it's kind of a clever way to add random effects and allow cities to have their own information from this model. And I allow to allow flexibility in the model. I'm going to have my G matrix be unstructured. So I have these 3 random effects. I have the random intercept, the general random intercept here, and then the random deviations off of the shape and the scale parameters. I have 3 random terms. And so my G matrix is going to be 3 by 3, and I'm going to allow it to be unstructured so that we have a flexible fit. There's some technical stuff here that you can probably spend a little less time on, but you can show the expected value of y given the random effects is equal to the probability of having rainfall for a given city on a given day. And then mu plus is the mean if it did rain. What's the mean rainfall? And then you can also make that city specific and day specific. Okay. And so using some basic theory, we can show the expected value of y. This is combining both parts of the model is equal to this, what I have here. So my last comment here on the slide is, you know, you could just report by city. You don't have to, or you could jointly report, sorry, back up a second. You can jointly report the probability and the mean and not force them to be combined, right? Because this distribution is probably going to be bimodal. And when a distribution is bimodal, you don't necessarily want to average that, but we may still find that information useful. It's just that you might also want to report those specific features of that bimodal distribution. And so we can do that by reporting the probability of rainfall and then what is the mean rainfall when it did rain. So you can report a bunch of different things here. A slide on deriving the variance of the amount of rainfall for this model. Show for homework. That's not a homework question that I'm actually going to give you. You can do it tomorrow night while you watch the election results. How's that? Just if you want something to distract you. I like some of the looks on your faces for that. But that may be a good thing to practice. It's not on the current homework, so I probably won't have it on any homework that I assign. But you could try it out, and it'll be a good practice question, I think, to look at that one. Some details on determining the covariance. I'll let you read that. The G, this is the unstructure that I'm using. The way that I parameterized it is actually to include correlation amounts here. So the way that I've written it, instead of, you know, we've often seen the covariance structure, you know, off diagonals might be sigma 0, 1, sigma 0, 2, or something like that. The way I've written it here has the same number of parameters, but allows us directly to report estimates for correlation between the terms. So for example, phi 2, 1 would be the correlation between that random intercept and the one for the random addition to the shape term. Okay, so it kind of just allows us to easily get things that we want to interpret for our model. Okay, so here is the data. I obtained this from one of the government websites. I think it was NOAA or something like that. So there's several cities, right? Atlanta, Chicago, Houston, New York, Phoenix, Sacramento, Seattle, and Aurora. So one of these things is not like the others. Do you remember that Sesame Street song, or do you guys, I don't know if you remember that, a few of you do. Aurora is not a big booming metropolis. It is actually growing. It's a surprisingly large city. I picked it because that's where Anschutz is, right? It's kind of gives us a nice comparison. So we have 8 cities, and I looked at the first 100 days of 2017 and got the rainfall amounts for these cities over those days. And it's actually precipitation. So it could, and it probably would include snow in some of these cities, like Aurora and New York at least. So I have that data, and here is the way that we fit the data. We can use proc-NL mixed. It's a very flexible procedure that allows us to specify our own model, and you guys already have some experience with writing code for NL mixed. So we define our, well, you know, we give it the parameter, you know, starting values again for the parameters in the model. We define our shape and scale pieces, and we have the random deviations for those. So our three random terms are expressed there. We have the logit link for the occurrence part of the model. And then we have, if there is positive rainfall, we know our density, we had shown that before. And so when we, this thing here is going to, this collectively specifies f of y, right, for the mixture. And what the beauty of it is, we can write it this way, which, because we have two parts to the model, right? We have the occurrence part and we have the intensity part. But this code actually allows us easily to say, if there's no precipitation, then this is what our log likelihood looks like. If there is precipitation, this is what it looks like. Okay, so the
Hey, Matt, I have a quick
code allows
question.
us to do that. Yep.
For your data, do you have one measurement per day?
Yeah.
So what is mu ij plus again? Is that the average precipitation across all the cities?
Yeah.
Okay.
Yep. So here's our, you know, we're basically building our likelihood, and we're specifying the covariance structure through G, and we've done that here, and I parameterized it so that we can directly get our correlation parameters between the random terms. And we can get our predicted values. So these would be the predicted rainfall amounts and predicted probability of occurrence, and then the combined elements of those we can get out of these predict statements. In a nutshell, here's our results. So we have to use Gaussian quadrature for this, but we're maximizing, we're approximating the true likelihood. You can see our correlation parameters between our random terms there, and estimates of our variances of our random effects, and our estimates of the shape and the scale parameters, and our intercept. So we get all of that here. And through the predicted values, we can compare the cities to each other. Now, one of the things that I didn't do is I don't have any terms in my model for day. And I tried that. For the data that I have was basically one season, it was in winter. Now, if I had extended that, then it would be more important to have day in the model, or something that accounted for changes over time. Here, I tried to keep it simple. So our mean is going to be the same across days, because I don't have a day term in the model. And we will get city-specific estimates by including the random effect deviations to the overall mean. Okay. But Jonathan, yeah, good point that, you know, yeah, so we get an overall estimate, and that's sort of across the cities. And then our city differences will be accounted for by adding the random effect estimates. So here's what we get. these are the means for each city. And I'm comparing descriptive to the model-based approach. And they're pretty similar, right? You notice that the model approach is a little bit lower on the cities that had high rainfall amounts like Seattle, Sacramento. Sacramento, it's not necessarily wet all the time, but in this season it was pretty wet. And then you have cities like Aurora and Phoenix that are drier. Okay, and Phoenix is probably generally a little drier than Aurora, but we live in a pretty dry climate here along the Front Range. You notice in the drier cities though, the model base is a little bit higher. So why is it a little bit higher for the cities that have lower rainfall and a little bit lower for the cities that have more rainfall? This is a question for you. This is my big question for the day. Let's see if you
less zeros.
No, I don't think it has to do with that.
Is this kind of like a weighted average where like the cities with the higher ones, the overall mean is getting pulled up towards the big cities, so the low ones are getting pulled up a little bit and the high ones are getting pulled down?
You're on the
a little
right
bit?
track, Carrie. So remember how we estimate random effects. How do we estimate random effects? We can express it, like you said, as a weighted average of subject specific, in this case city specific information, and an overall average, right? And we talked about how random effect estimates, if you use empirical Bayes methods, they tend to be shrunk to the mean. And so it's not a surprise that we're going to the lower cities are going to be shrunk more, to the middle, and the higher ones are going to be shrunk more to the middle. That's just a nature of empirical Bayes estimates. They tend to kind of move towards the middle a little bit. The more information you have on specific cities, the less that is going to happen. But you will notice that if you compare it to just descriptive amounts. Okay. Now the last thing I want to show you is we can get probability of precipitation, and then we have mean precipitation on days with positive amounts. So we're breaking down the information here into pieces, and it gives us interesting information, right? So we know that Seattle has much higher probability of precipitation. But if you look at the mean precipitation on days when there was precipitation, it's not as high as Houston and Sacramento. And what is that telling us?
Is that just saying that
Seattle just has
Go ahead, Elise.
Seattle just has a constant drizzle.
Yeah. You're going to say the same thing, Jonathan? Okay, so in Seattle, it's just like a consistent spray of drizzle, right? And so you get a lot of total precipitation, and you get a high chance of precipitation. But in Houston and Phoenix, when it does rain, and it tends to rain really hard and a lot, okay? And Aurora, we just happen to have kind of a dry snap, I think, in those 100 days that I collected the data on. Like I said, it does tend to be dry around here, but a little drier than normal, I think. And so what would you do? The next step, I think, would be to add more data so that you can get more reliable estimates. So my last question is, why, if we get estimates from this complicated model that are not that different from descriptive, why even do the model?
you don't really know that until you fit the model.
On the right track. So you don't really know what?
You don't really know that fitting this model is worthless until you fit the model.
Yeah, okay, I'll accept that. The other thing that I was thinking is that you can't really do inference if you just have the descriptive statistics. We can't make statistical comparisons and make inferential statements, just based on the descriptive statistics. Okay. I think I got through okay. I'm going to try to figure out why my pen wasn't working and maybe get that going by Wednesday. So Wednesday we'll talk about interpreting parameters in longitudinal models. Next week the quiz, and then talk about missing data. And I will also be around Wednesday after class if you have anything you want to discuss. So have a nice day, and we'll see you guys Wednesday.